Hello friends, our subject operating system has Unit 5 Memory Management for 10 marks. Today we will see part 1 of it. The course outcome 502.5 is Calculate efficiency of different memory management techniques, and unit outcomes are Describe the working of the specified memory management function, explain characteristics of the given memory management technique, write algorithm for the given page replacement technique, calculate page fault for the given page reference string. These are the contents of Unit 5. Basic memory management, partitioning, fixed and variable, free space management technique, bitmap, linked list, virtual memory, introduction to paging, segmentation, fragmentation and page fault, page replacement algorithm, first in, first out, optimal page replacement, least recently used algorithm. Today we will see basic memory management. Basic memory management. An executing process must be in main memory. The main memory must accommodate both operating system and various user processes. The main memory is usually divided into two partitions, one for the resident operating system and other for the user processes. The operating system can be placed in lower memory partitions with the interrupt factor. Usually, we want several user processes to reside in the memory at the same time. Therefore, we need to consider how to allocate available memory to the processes that are waiting in a queue. Relocation registers are used to protect the user processes from each other and from the changing the operating system code and data. Base register contain the value of the smallest physical address, and the limit register contain the range of the logical addresses. Each logical address must be less than the limit register. Memory management unit maps the logical address dynamically. Memory management technique. Although the following simple memory management techniques are not used in modern operating systems, they laid the ground for the later proper discussion of the virtual memory. Fixed partitioning, variable partitioning, simple paging, simple segmentation. Fixed partitioning. One of the simplest methods for allocating the memory is to divide the memory into several fixed size partitions. Each partition may contain exactly one process. Thus, the degree of multiprogramming is bound by the number of partitions. In this multiple partitioning method, when a partition is free, a process is selected from the input queue and is loaded into the free partition. When the process terminates, the partition becomes available for the another process. This method was originally used by IBM OS 360 operating system. It is no longer in use. Fixed partition can be of two types, equal size partition and unequal size partition. From the diagram, you can see that the first diagram shows the equal size partition where 8 M size partitions are there, and the second diagram shows unequal size partition in that variable different size partitions are made. In fixed partitioning scheme, the operating system keeps a table indicating which part of the memory are available and which are occupied. Initially, all the memory is available for user processes and is considered one large block of available memory, a whole. When the process arrives and needs memory, systems search for a whole large enough for this process. If the sufficient memory is found, the process is allocated to it and the rest of the memory will be available to satisfy the future request. If the leftover space in the partition after program assignment is small, it is kept with that process It is called as internal partition. When the process terminates, it releases its memory, which can be used by the other process. Equal size partition. When all the partitions of the equal size, there is no special effort required to decide which partition to use. If all partitions are assigned by the block processes, choose one process to swap out to make a room for the new process. Unequal size partition with multiple queues. As shown in diagram, for each partition, there is individual queue present and the processes from that individual queue will be placed into that respective partitions. It assigns each process to the smallest partition within which it will fit. A queue exists for each partition size. It tries to minimize internal fragmentation. The problem of using multiple queues is some queues might be empty while some might be loaded. So, there is a next type, unequal size partitioning using a single queue. As shown in diagram, there is a single queue for all the partitions and the processes which are there in the queue according to their size allocated to the respective partitions. It will load a process into the memory, which is the smallest available partition, and holds the process. It increases the level of multiprogramming at the expense of internal fragmentation. Advantages: it is simple to implement, little operating system overhead, and disadvantages: inefficient use of memory due to internal fragmentation. Maximum number of active processes is fixed. Variable partitioning. Partitions are created dynamically. When a process enters in the main memory, it is allocated exact size that is required by that process. So in this method, the partitions can vary in size depending on the memory space required by a process entering in the main memory. The operating system maintains a table which parts of a memory are available and which parts are occupied. When new process arrives, it needs the space. The system searches for the available memory space in the main memory. If it is available, then the memory is allocated to the process by creating a partition in the memory. Like this, depending on the size of processes and available memory, partitions take place in the main memory. This is the example which shows how the processes are allocated into the memory. So initially there are three processes, process 5, process 8 and process 2 are stored into the memory. Now the process 8 has completed its execution, so it will be transferred to the backing storage. Now there are only two processes, process 5 and process 2 present in the memory. Now the new process, process 9, store into the whole of the memory, free whole of the memory. Now it will create another small hole. At that hole, we can store the process 10 and again there is a smaller hole created. So the diagram shows how the memory can be partitioned variably, that is dynamically. To explain this, we will see one example. Consider that there is total memory size of 64 megabytes and the operating system size is of 8 megabytes and there are total 5 processes P1, P2, P3, P4 and P5. According to the size, the 20 megabytes, 14 megabytes, 18 megabytes, 8 megabytes and 14 megabytes. Now, the time required for the execution of the respective processes is also specified. Now suppose we want to execute the process P1. So initially the memory 8 megabytes of memory will be allocated to the operating system. So the remaining part will be 56 megabytes for the user processes. So the process P1 is allocated to the memory. So remaining part of 8, that is 36 megabytes, will be the whole. So the second process, process 2, will be allocated to that free whole. Now the size of the process 2 is 14 megabytes. So the whole size will become 22 megabytes. So our third process, process 3 of size 18 M, can also be occupied into that free hole, creating the smaller hole of size 4 megabyte. Now the next process P4 cannot be allocated, so it will wait to complete one of the process execution. As the process 2 time is 5 milliseconds, its execution will complete and its area, that is 14 megabytes, whole will be created. Now the process 4, which is of 8 megabyte, can be stored at that whole location. So its execution may start. It will create another hole of 6 megabyte. So now there are two holes. One is of 6 megabyte and another is of 4 megabytes. So the next, the process 1 has completed its execution. Now the process 5, which is of size 14M, can be stored at that location, creating another third hole of size 6M. Now at this location, if there is one new process, process 6 will appear into the system with the size 10M. We cannot execute that process even if the free memory, that is 6 megabytes plus 6 megabytes plus 4 megabytes, that is total memory 16 megabytes is available. Still we cannot execute the process of size 10 megabytes as the memory is not continuous. So this is called as external fragmentation. So for the variable partitioning, this is the drawback. So we will study the term external fragmentation and internal fragmentation. The total memory space exists to satisfy the request, but it is not contiguous. That, as we have seen in that example, it is called as external fragmentation. And what is the internal fragmentation? Allocated memory may be slightly larger than the requested memory. This size difference is the memory internal to the partition but not being used. So it is called as internal fragmentation. Reduce the external fragmentation by the compaction. For that, shuffle the memory content to the place all free memory together in one large block. Compaction is possible only if relocation is dynamic and is done at execution time. The I/O problem is that the large job in the memory while it is involved in I do I/O only into the OS buffers. So this is one of the example of the compaction. As shown in the first diagram, there is the fragmented memory. In that we cannot store our program. So compaction is done. Due to that, the occupied memory will come at the one location and will create a big hole. Into that we can store our processes for the execution. So the next topic is dynamic storage allocation algorithm. These are the four allocation algorithm that can be used to allocate the memory in the variable partitioning. First algorithm is first fit. allocate the first hole that is big enough. The first fit state that allocate the first hole that is big enough to store our process. The second algorithm, next fit, same logic as the first fit, but start the search always from the last allocated hole. So, the first fit and next fit, both algorithms work on the same logic, that is the allocate the first hole that is big enough to store our process. But the difference is that first fit search always start from the beginning and the next fit search will start from the where the previous search is stopped. Okay. So the next allocation algorithm is best fit. Allocate the smallest hole that is big enough to store our process and must search the entire list unless the ordered by the size. This produces the smallest leftover hole. This produces the smallest leftover the hole. So the best fit strategy follows the thing that it will search the smallest hole which is big enough to store our process. The worst fit strategy is opposite to the best fit. It allocates the largest hole which is big enough to store our process. And this must also require the search the entire list and search the largest hole from the list and which is able to store our process, and this produces the largest leftover hole. This best fit creates the smallest leftover hole and the worst fit creates the largest leftover hole. So the first fit and best fit better than the worst fit in terms of speed and storage, because in case of best fit and worst fit we need to search entire list, search for the smallest hole or largest hole from the list. So first two are the fastest. So here is the one example that will clear more about the allocation algorithm. In the first diagram, there are allocated blocks and free blocks. Allocated blocks are shown with grey color and free blocks are shown by the white color. So there is one also indication of the last allocated block which is of size 14 megabytes. Okay. So this is the last allocated block which will require us for the next fit logic. Okay. Now our aim is to store the 16 megabytes of block into the memory. Now we know what are the free blocks. So there are free blocks of size 8M, 12M, 22M, 18M, 8M, 6M, 14M and 36M. Now we want to store 16 MB block into the memory. Now if we will follow first fit strategy, so always the search will start from the beginning. So our first is 8M will not allow, 12M will not allow, 22M, yes, it can work. So the 16M will be placed to that 22M hole and the remaining leftover will be 6M. So the first fit as shown in the next diagram, after diagram, the first fit will allocate the block which is the hole which is of size 22M with creating the new hole of size 6M. So the next algorithm is the next fit. Now as our previous search stopped at the location of 14M, so as shown in this before diagram, 14M is allocated in the previous search. So now for the next fit our search will start by that particular location. So we will search from the 8M. So we cannot store 16M into 8M. So it will not allow. For 6m it is not allowing. 14m it is not allowing. So it will allocate 36m. So in the next fit algorithm, it will select the whole of 36m size. So it will create the new hole of size 20 by allocating 16m to the 36m. So the next fit is shown there in the after diagram. Now suppose we are following best fit strategy. For that we will have to search the hole which is big enough to store the process. The smallest hole which is big enough to store our process. So searching will start from the first. It will search the whole list and will select the hole which is of size 18m, which is big enough to store our process and which is the smallest one from the list. Okay, so the best fit will allocate the hole of size 18m and creating the new hole of size 2m. Also, the next one is worst fit. Now the worst fit will be the same as the next fit because it will select the biggest hole from the list to allocate the process. So the biggest hole is of size 36m. So in case of worst fit, it will select the hole 36m to allocate the process of the size 16m. So thank you.